Hello everyone, this is Math 68 Probability Theory. I am Diana Rose B. Rebucan, and we will be talking about binomial distribution. So if a random variable x is defined to have a binomial distribution if the discrete density function of x is given by f sub x of x equals f sub x of x and np equals n taken x p to the power of x q to the power of n minus x, where x is equal to 0, 1, up to n. So we have here figure 3, the binomial densities. We have x values and also n and p. So if we're going to substitute this to the given formula, which is n taken x, p to the power of x times q to the power of n minus x, we will get these values, where the parameters n and p satisfy p less than or equal to 1 but greater than or equal to 0, and n ranges positive integers. And always remember that q is equal to 1 minus p. A distribution defined by the density function given is called a binomial distribution. So now let's proceed to theorem 3. If x has a binomial distribution, then the expected value of x is equal to np, variance of x is equal to npq, and the moment generating function of x is equal to q plus pe to the power of t quantity to the power of n. Let's proceed to the proof. Since it is a discrete density function, we will use the summation formula. Summation of e to the power of dx times n taken x times p to the power of x times q to the power of n minus x, where x is equal to 0 up to n. Let's just put a beside p. So the summation of n taken x, pe to the power of dx, q n minus x, where x is equal to 0 up to n. So by Appendix A, equation 15, the binomial theorem, it is written there that a plus b to the power of n is equal to summation of n taken j, a to the power of j times b to the power of n minus j, where j is equal to 0 up to n. So here, our a is pe and our b is q. So we will come up to an answer that moment generating function of x is equal to pe to the t plus q to the power of n. So we already get the moment generating function. So to get the expected value of x, we will first get the first derivative of moment generating function. So what we're going to use is the chain rule. So n quantity pe to the t plus q to the power of n minus 1 times pe to the t. So the first derivative function of x, the first derivative of generating function moment generating function is equal to np e to the t quantity p e to the t plus q to the power of n minus 1. So we're going to let t equals 0. So expected value of x equals n m. We have here np e to the power of 0, p e to the power of 0 plus q to the power of n minus 1. So e to the power of 0 is equal to 1. So we have here np times p plus q to the power of n minus 1 is equal to np. P is equal to 1 minus q, so plus q to the power of n minus 1. We can cancel this, and this is already 1. So our moment generating function of x is equal to np. So our first derivative is equal to np e to the t times p e to the t plus q power of n minus 1. In getting the variance, we first get the second derivative of the moment generating function. So what we use here is the product rule. So np e to the t times n minus 1 times p e to the t plus q to the power of n minus 2 times p e to the t plus np e to the t times p e to the t plus q to the power of n minus 1. We'll just have to combine like terms, so we will get n times n minus 1 times p e to the t squared times p e to the t plus q to the power of n minus 2 plus n p e to the t times p e to the t plus q to the power of n minus 1. To get our goal, we let t equals 0. So we have to let t equals 0. So we have here n times n minus 1 times p e to the power of 0 squared times p e to the power of 0 plus q to the power of n minus 2 plus np e to the power of 0 times p e to the power of 0 plus q to the power of n minus 1. So we have our knowledge that e to the power of 0 is equal to 1. So we will get n times n minus 1 times p squared times p plus q of n minus 2 plus np, the quantity p plus q to the power of n minus 1. So we know that this and this will be equal to 1. So this will be 1 and 1. So our final answer will be n times n minus 1 p squared plus np.